In October 2017, a telescope in Hawaii picked up an object moving too fast to belong to our solar system. It didn't behave like a comet. It didn't behave like an asteroid. 6 years later, scientists still can't agree on what it was. On October 19, 2017, astronomer Robert Weryk was analyzing data from the Pan-STARRS-1 survey telescope at the Haleakala Observatory in Hawaii. He noticed a faint point of light moving at an immense speed across the frame. Initially designated 2017 U1, this incoming visitor had already reached perihelion on September 9th, passing within 0.25 astronomical units of the Sun. It was well inside the orbit of Mercury weeks before its discovery. As global tracking assets confirmed its path, the orbital mathematical models revealed its true nature. It possessed a hyperbolic trajectory with an eccentricity of roughly 1.2. In orbital mechanics, an eccentricity greater than 1 confirms that a body is not gravitationally bound to the Sun. Its trajectory, rather than its physical appearance, proved its interstellar origin. To mark this moment, the International Astronomical Union updated its catalog pathway to 1I 2017 U1 and approved the Hawaiian name Oumuamua, meaning a scout or messenger from afar. As telescopes worldwide tracked this departing speck, astronomers encountered a series of unprecedented physical anomalies. Because Oumuamua remained a point source, too small for direct imaging, researchers relied on light curve analysis to decode its nature. Photometry from the Gemini North Telescope and the Palomar 60-inch revealed extreme brightness variations fluctuating by a factor of 10 every 8.67 hours. This massive swing implies a complex tumbling end-over-end rotation rather than a simple clean spin. To match these light curve cycles, mathematical models require a highly elongated cigar-like shape with an estimated length-to-width ratio between 6:1 and 10:1. No known native asteroid or comet in our solar system exhibits such an extreme physical profile. Assuming a low reflectivity typical of cometary surfaces, planetary scientists estimate its length between 100 and 400 meters. Reflectance spectra from the Very Large Telescope showed a deep reddish surface color consistent with organic compounds altered by eons of heavy cosmic ray exposure in the cold interstellar void, resembling the radiation-scarred surfaces found in our own outer Kuiper belt. During its pass within 0.255 astronomical units of the Sun, Oumuamua experienced intense solar heating. At this close range, frozen gases should have sublimated, producing a bright, expanding coma and a visible dust tail. Yet, targeted imaging from the Keck Observatory in Hawaii detected no dust emission. Spectroscopy from the European Southern Observatory's Very Large Telescope confirmed the absence of carbon and cyanide gases, setting the mass loss limit at less than 1/10,000th of a kilogram per second. Thermally, the object behaved like a completely inert asteroid. This lack of volatile activity presented a stark physical contradiction. If the object possessed no ice to vaporize under the Sun's heat, it should have behaved like a quiet, dead rock traveling along a predictable, gravity-driven path. To trace the departing path of the object, astronomer Marco Micheli coordinated an international tracking effort using 30 ground and space-based observatories. For months, this campaign gathered precise positions to map the trajectory as Oumuamua faded from view. When Micheli and his team analyzed the compiled coordinates, they found that the orbital path deviated from a purely gravity-driven course. The astrometric measurements revealed a systematic drift. In a 2018 study published in Nature, Michele's team reported a small but distinct non-gravitational acceleration, pushing the object radially outward, away from the Sun, at roughly 5/millionths of a meter per second squared. Mathematically, this anomaly was detected at a high level of statistical significance. In planetary science, a radial push of this scale typically points to the physical recoil of sublimating gas and dust. Yet this standard interpretation immediately ran into a wall of evidence. The previous targeted observations had already confirmed a complete absence of any visible cometary tail or outgassing material, turning a minor orbital drift into an unresolved physical contradiction. In 2020, astrophysicists Stephen Desch and Alan Jackson proposed that Oumuamua was a fragment of solid nitrogen ice, chipped off a Pluto-like exoplanet. This model, drawing on analogies to Pluto's Sputnik Planitia, explains the missing Coma puzzle because evaporating nitrogen gas is invisible to optical instruments and releases no dust. However, nitrogen ice is highly volatile, and critics argue such a fragment could not survive a flight of millions of years through interstellar space without eroding completely. Another hypothesis, introduced in 2019, suggested a molecular hydrogen ice iceberg. Hydrogen outgassing would easily generate the observed non-gravitational acceleration while remaining entirely undetectable to our instruments. Yet, thermodynamic calculations quickly stalled this idea, showing that solid hydrogen evaporates at just 6 Kelvin, meaning the iceberg would have melted long before reaching the inner solar system. Alternatively, astronomer Amaya Moro-Martin proposed an ultra-porous, fractal dust aggregate model. This theory envisions Oumuamua not as a solid rock, but as a fluffy, microscopic dust cloud with a density below 1,000th of a gram per cubic centimeter. This extreme lightness allows solar radiation pressure to push the object without any outgassing. Still, researchers question if such a fragile, porous structure could survive interstellar space without collapsing under cosmic ray compaction. In November 2018, astrophysicists Avi Loeb and Shmuel Bialy published a paper in the Astrophysical Journal Letters proposing a technological explanation. They argued that the measured non-gravitational acceleration was the result of solar radiation pressure pushing a thin, artificial light sail. If Oumuamua was an engineered, highly reflective sheet less than a millimeter thick, sunlight alone could drive it along its outbound path without any visible outgassing or dust tail. Loeb expanded this hypothesis in his 2021 book, Extraterrestrial, suggesting the object might be a probe or a piece of discarded technology from another civilization. The proposal faced immediate and intense pushback within the scientific community. Most astronomers criticized the claim as premature and unsupported by direct observations, even though it could not be mathematically disproven. Critics maintained that all natural possibilities must be exhausted before invoking an artificial origin. In December 2017, the Breakthrough Listen project pointed the 100-meter Green Bank telescope in West Virginia toward Oumuamua. The team conducted a 68-minute scan across a wide range of radio frequencies spanning 1 to 12 gigahertz, searching for artificial signals or narrow-band technosignatures. This direct observational test aimed to verify if the object carried active transmitting technology. The analysis returned a null result, showing no signals above the telescope's highly sensitive detection threshold. While this search ruled out powerful active radio transmissions directed toward Earth, it could not eliminate passive or non-radio technologies. By January 2018, Oumuamua faded beyond the reach of ground-based telescopes. The Hubble Space Telescope and the Spitzer Space Telescope captured the final fleeting data points before the object slipped into the outer solar system. It is now traveling beyond the orbit of Saturn on a permanent trajectory back into interstellar space, leaving behind an incomplete scientific record. In 2019, a NASA-backed review evaluated the competing models, leaning toward the natural nitrogen ice theory, yet concluding that no single hypothesis fully resolved the non-gravitational acceleration. Later that year, the discovery of 2I Borisov intensified the mystery. Borisov behaved like a classic volatile rich comet with a prominent dust tail and a rich chemical spectrum, presenting a stark contrast to Oumuamua's dry, inert profile. This difference confirms that interstellar visitors are diverse. Because Oumuamua was detected late and departed quickly, astronomers were left with a frustratingly limited window of observation. The next interstellar visitor will require a global, rapid response network ready to deploy the moment a new trajectory points back into the dark. Today, Oumuamua drifts in the deep dark, beyond the reach of our instruments. As next-generation observatories scan the skies, they prepare for the next interstellar visitor. The question isn't what we missed, but whether we will recognize the next truth when it arrives. Share your thoughts below.